it's my great pleasure to introduce Julian. I've met him a long while ago, I think in Oxford, and Julian now is a professor at Cambridge, and he has obtained numerous outstanding results and about Ramsey numbers, and the talk that we had last semester on sphere packing. It's also with Julian, and many great results. He has given a talk on this seminar before on polynomials, which was very interesting. And yeah, it's a pleasure to have him. So, Julian.
Lovely. Yeah, it's a pleasure to be talking in front of you today. Yeah, feel free, of course, to ask questions, slow me down. I think I'm a little bit ill, so it might be good to slow me down actually a bit. Good, okay, so I'd like to talk about the Ramsey numbers, and I'll just jump in and define what those are. So the main object of study is R of k an integer, which is just the minimum, and such that every red-blue coloring of Kn, or the edges of Kn, contains a monochromatic case of K. And here I've snuck some notation in on you. So this, if you're not familiar, this is now just the complete graph on n vertices, and of course here's the complete graph on k vertices. It might, while I'm here, we won't talk about it so much, but I will make a few remarks on the off-diagonal Ramsey numbers. So here there's a symmetry in the two colors. We're either looking for a clique of the same size in either color, but we could also imagine the off-diagonal Ramsey numbers. So this is just the minimum n, such that every red-blue coloring of Kn either contains a blue case of L or a red case of K. So this is L. This is the blue color, and this will be the red color. Okay, so of course, RKK is R of k, which is sometimes why it's called R of k, sometimes called the diagonal Ramsey numbers. But mainly we'll be just talking about R of k after this talk, beyond a few remarks. So this is a well-known problem in combinatorics, and it goes back all the way to Ramsey, who proved that these numbers indeed exist. So, oops. So theorem, and this is in 1930. So it's not at all obvious actually that they exist, but Ramsey proved that they do. Right, so there always exists some large enough n for which we can find this phenomena holds. The first good bounds. Or first, maybe I should say exponential bounds. Ramsey actually had factorial bounds, which is a bit odd, but it's kind of interesting. But the first exponential bound was given by Erdős and Sekeres. A few years later. It seems actually that they independently discovered the theorem, and then someone had told them that actually Ramsey had this idea before, and they proved that R of k basically is at most 4 to the k. In fact, they did something a little bit better, which I'll get into later. Okay, so I think it's like a good warm up, just if you haven't thought about this well, let's just prove this bound, and we'll get our help us fix our understanding here. So let's give it a proof, and the proof will really just be by a picture. So what does this mean? R of k is at most 4 of k. If you give me a graph, a complete graph on n vertices, so this is my pool of n vertices, I can find where n is bigger than 4 to the k, then I can find this monochromatic clique on k vertices. Okay, so here we go. what I'm going to do is I have some coloring, red-blue coloring in this world here. I'm going to take a vertex. I'm going to pull it aside. And now half my world, sorry, there'll be some vertices, this vertex will be joined to some vertices in red and to the rest in blue. Like this. Okay, one of these is at least 50% of the world. Let's just say red for now. So say this is at least 50% of the world. What I'm going to do is just delete this. I'm going to put this vertex into my red hand and continue the process with this bit. Okay, so what's just happening, and this will sort of set us up for later, I'm going to have a fistful of red vertices, a fistful of blue vertices. These are going to be all joined to each other in red and blue. There's going to be some remaining reservoir of vertices like this. These will be joined completely from here to here in red, and these will be joined completely from here to here in blue. And what's going to happen, the algorithm's going to run along, and I'm going to maintain this picture. So at each stage, I just repeat exactly what I saw in the first step. So I take a vertex here, I pull it aside. Let's move this here. I pull it aside. Now it's joined to some vertices in red, some vertices in blue. Okay, and now say this is at least 50% of the remaining world. I'll shrink X to be this bit here, put this vertex into my blue bit, and I've maintained this picture. And I'm always increasing either A or B by 1. Okay, so how does that give a bound? We just need to track what's happening. So we started with n vertices, and at every stage, the algorithm is going to halve the size of the world. And how many times are we going to have it before we fill up one of these to k vertices? Well, one is until basically k plus k minus 1 steps, right? Just by pigeonhole, I have to eventually fill. So this will be, I'm just going to be lazy and write 2k. And this better never sort of run out of space for the algorithm to work. So this better be 1 the entire time, at least 1 the entire time. And now we see that if n is bigger than 4 to the k, then we actually find the clique. You'll see there's actually a slight cheat in here because I also remove a vertex, but okay, we're not gonna care about this slight cheat. Okay, so this is a very nice upper bound. But the question is it any good at all? Right, so just some exponential bound out of nowhere. And in 1935, it was actually really unclear what the right answer was. And if you look at the literature, it's actually really, people are unsure about what to guess for the right answer. And you might think, I'll do a little bit of more here. So background is you might think that it's actually much, much smaller. So here, if I just give this problem to you, you've never thought of it before, you might come up with the following lower bound. Okay, so what does it mean to give a lower bound? I need to produce a coloring on a graph on n vertices, and I want n to be as large as I can possibly make it. Okay, so here's an idea. Maybe the first idea one would think of is you take clusters of size k minus 1, everything joined to everything in red, and then you join everything between these guys all in blue, and those k minus 1 clusters in total. Okay, so how many vertices are there? And here is going to be k times 1 squared, and I claim that there's no monochromatic clique in here. Okay, so what if there's a red clique? Then it clearly has to be all in one of these clusters, but the clusters have size k, at most k minus 1. If it's a blue clique, then they all have to be in different clusters. Okay, but there's only k minus 1 clusters. Okay, so it's a candidate, and this shows that R of k is bigger than k minus 1 squared plus 1. Okay. So this actually seems like a pretty nice construction. You have this somewhat very wasteful looking upper bound, right? So I think it came as a bit of a shock in my understanding when Erdős actually proved that exponential is the right answer here. So this is Erdős in 47. who prove that R of k is at least 2 to the k over 2, actually for all k. So actually, this exponential behavior is correct. And the proof is sort of completely different than anything, not completely different, but it was a new strategy at the time, which was to use randomness, right? So this is actually one of the, not the first, but an early application of, and very influential application of the probabilistic method in combinatorics. So let me just quickly, it might make sense just to sketch the proof, just to get some, it's essentially only 2 lines. Once I say use randomness, it's almost already done. So let's just quickly sketch the proof to get some feeling. So what do I need to do? I want to produce a coloring on a graph on this many vertices, okay? And my coloring chi will just be chosen uniformly at random among all such colorings, i.e. just flip an independent coin for each one, then you're red, blue accordingly. And all I would like to do is show that the probability that there exists a mono k sub k is less than 1, right? Okay, so what is that? There's n choose k possible k sub k's, right? So this is basically just a big union bound over all possible k sub k's. So there's n choose k possible ones. And once you fix a particular k sub k, whatever, say the first k elements, well, then I can exactly write down the probability that that's monochromatic. So it's 1/2 to the number of coins / edges that have to come up heads or all tails. So it's 1/2 to the k choose 2. And actually, there's actually also a factor of 2 because all heads or all tails. Okay. And now this is just a matter of math. I just claim that this is less than 1. And then this is a proof if n is equal to this. Let me just quickly estimate it because I'd like to make a further observation here. So this is this until I'm tired. Like this, and I just want to get a feel for the numerics a little bit here. So this is 2 to the k, I'll put a 2 there as a root 2, sorry. Yeah, that's okay, that's correct. Oh my goodness.
Square root, yeah.
Yeah. Crucially. Yeah, thank you. Right, so the point is basically what's happening here. Now you just see the numerics coming out of this calculation, right? So this is just, if this n is 2 to the k over 2, then this n is exactly canceling with this. And actually we have this extra k here that's like change. So this is less than 1. This whole thing is much less than 1. So this whole thing with a little bit of is less than 1. So this is actually a genuine proof of this lower bound. Let me just remark here that we actually prove something slightly stronger here, right? So it actually proves that R of k is at least, if you do this numerics a little bit more carefully, this is giving 1 over root 2 times e plus little o1 times k times 2 to the k over 2. Interestingly, the only improvement to this lower bound to date, so this was in the late 40s, the only improvement so far is that this root 2 has been moved upstairs here. So this is the current state of the art on the lower bound for Ramsey number. And this is using just a local lemma. So this is, it's one of these things that it seems like even improving this humble constant out here is already is proving itself to be an interesting problem. Good. Okay, so what's happening? So R of k is at most 4 to the k, as we saw. And we've also seen that it's at least 2 to the k over 2. Nice. And so, so we feel good about ourselves, that we understand this exponential, but the big question remains is like, well, what's happening in between these two ranges? And there's actually like quite a bit of interesting mathematics that, not really mathematics, but mystery between these two ranges. Okay, so let me just quickly say a few things about improvements. So I've actually completely said everything that's known about the lower bound. So random is slightly improved by local lemma, and that's it. Okay, so for the upper bound, there's been a little bit more improvement.
Julian, actually, I can ask you a question, a little bit side question. So I forgot. So what was the reason Ramsey was interested in this?
So he was interested in some question like in logic and formal systems, and I can't state to you the problem actually.
Okay.
Yeah. Yeah, so I think he was even using like the hypergraph version of it for some reason, or what we would call hypergraph version.
Okay.
Yeah. Okay. So what's known for the upper bound here? So actually, Erdős and Sekerish prove something a little bit better than what I said before. If you track things carefully, so for some constant, you get this extra root k. This is obviously in the 30s, 35. And then that was basically the state of things until independently Rödel improved it by stuck an extra log factor in here. And this is in the 88. And Andrew Thomason improved it by a polynomial factor. Andrew Thomas. This was
4 to the k.
4 to the k. Thank you. Okay, so in one sense, this seems like a humble improvement, but actually already in this paper, there's this really interesting sort of notion of quasi-randomness that was born for graphs in the work of Andrew Thomason that was developed further. And then this notion was pushed quite a bit further by Conlon, who sort of showed that you can put any polynomial factor here. So he proved k minus log k to the 2 minus little o1. This is David Conlon. Like at 06 or something, maybe 08. Anyway, maybe 06. And then this is really pushing on these quasi-randomness ideas, developing this method quite a bit further. And then this was pushed sort of to its natural limit by Sa not too long ago. Oops, there should be a constant here. And 23, who sort of proved the optimal version of this result of Conlon, this method of Conlon. Okay, so these are actually all, none of them is actually moving the exponent, but I would just like to stress that these are actually all have really nice ideas in them, which have been influential elsewhere. Okay, so 2 years ago, joined with Marcelo Campos, who I guess talked recently in the seminar, Simon Griffiths, and Rob Morris, and myself. We managed to obtain the first exponential improvement on the diagonal Ramsey numbers. For some fixed C. Okay, so this was, I guess this was basically 2 years ago that we finished this paper, and it was, it's something we had been working on for a long time, but at the end, we still had some reservations about our proof. So let me sort of like to sort of spell out our what we felt were shortcomings of this paper and this proof. So one thing is that the proof didn't naturally generalize to more colors. So proof not, whoops. So this is actually not such a strange thing in Ramsey theory. There's lots of things that we know for two colors, but then pushing beyond it seems to require some more ideas. Sometimes completely open problem, for three colors. But we were a bit disappointed that it sort of only worked for two colors. Something maybe a little bit different is we also were very guided by a certain sort of geometric intuition in this paper. But at the end of the day, we completely lost, at the end of the day, like the paper, the final paper, completely lost this connection with geometry. We sort of had this interesting geometric conjecture that we were trying to work on, and we weren't able to solve it directly, but sort of did something in situ that was good enough to make it work. So, but we were kind of excited that we were building some kind of intuition and connection from something seemingly different, but then we were sad that we lost it. So lost any connection with geometry. And of course, I'll say more about that in a second. And then maybe most personal is, one likes to feel like in some sense they, deserve their own success. And there's a sense in which we felt like we got a little bit lucky with this paper. So just to say something about that, to make the case against us, is what we did is we actually started from the diagonal Ramsey numbers, and then we related this to the off-diagonal Ramsey numbers. So this is R of k, and then we related to something like 9/10 k, k, and then got from here to got from these off diagonals to victory. This step here, actually, we run at a loss. Our algorithm runs at a loss. So actually, if you chain this step with just a running Erdős-Szekérys algorithm from this step, it gives you a very long proof that the Ramsey number is at most 4 plus constant to the k. So, but what our algorithm does very well is it works very well in the off diagonal. So actually, we run much more efficiently, or significantly more efficiently, from here to finish, and this win beats out this loss. So it feels a little bit lucky, like, okay, you were losing here and you're winning here, and the win just sort of managed to beat out the loss. But we don't maybe have like a really good reason for that, beyond that we believe that this is true, but it looks a little bit lucky. So I'll put this shortcoming like this. Did we just get lucky? Okay, so what I'd like to talk about today in the remainder is the following theorem. I guess this was two years ago, 2 springs ago that we finished, and then last spring we got together. So this was CGMS, and sort of rehashed a new approach, based on our method. And then we sort of took this approach and workshopped it with a bunch of people. So this is along with Paul Ballister, Bela Bullabosh, Owen Hurley, and Marius Tiba, and managed to actually push this new approach through. So the theorem that I'll write down is actually an exponential improvement for the multicolor Ramsey numbers. Okay, and of course, this is just what you think they are. So for every R bigger than 2, the R color Ramsey number. So this is now I'm allowed to color with, say, R is 3. Now I'm allowed to color with red, blue, green, and I have to find a clique in one of these colors. then we have an exponential improvement. Sorry. So for every r, there exists some delta depending on r, so that this is e to the minus r. Whoops. Delta times k. And now this is just r to the r. Okay, so I said exponential improvement on what? This bit is the exponential improvement, right? And this is actually was the previous best known thing. And in fact, it's very easy to see. So this is the exact analog of what you would do if you just ran this Erdos-Sekresh argument with R colors. Right, so this is the improvement bit. This is exactly what you would get if you just ran Erdos-Sekresh with R colors, right? So you now at every stage, you take a vertex aside, there's R different neighborhoods, right? You take the one that's at least 1 over R. So that's accounting basically for this R, because now you're losing a factor of 1 over R in each step. But now you have to have R different colors that you're tracking all at once. So that's accounting for this R here. So this is the Erdos-Sekresh argument and the begin exponential improvement. Okay. Okay, so that dealt with one of what we felt was a shortcoming here. And as we'll see in a second, we actually regain a kind of connection to geometry. So this was not the original conjecture that we were stuck on for a long time that was kind of behind the original, but a new sort of one that we developed, which I'll talk about in a second. Okay, and did we get lucky? Well, who knows? Maybe we got lucky again. But I think that I mean, you can be the judge of that, right? So I would like to sort of present this as a bit more motivated. You can really see right in the algorithm sort of where you're winning over Erdos-Sekresh. So, for example, we're always staying on the diagonal here. There's no sort of funny business going through the off diagonal where you're losing and then winning. You can kind of it's much more clear that it is giving a more efficient algorithm.
And in terms of the bound, is it better or worse than the previous proof? Like if you actually write down the constant for the
this
two colors.
Is a good question, and that also reminds me. I forgot to mention that there was a paper recently that really optimized our bound. That got R of k is almost 3.8 to the k by Gupta, Diane Noren, and Wei. So this was actually them working on optimizing our first paper. Here I actually haven't checked the numerology. I don't think it gives as good as 3.8 though. Of course, one could maybe combine techniques or something like that, which I certainly haven't even begun thinking about. So, yeah. So sorry. Let me actually just say also here, just a quick. Just to fix ourselves with these numbers, our understanding here. So I mentioned that the Erdos-Sekresh originally proved this upper bound, and we get an exponential improvement. Okay, well, what's the lower bound? There's actually another interesting mystery here, where the best known lower bounds are no longer random. And the best constructions are giving something like c to the r times k. There's actually been some interesting work in here, which is, okay, so the earliest constructions are basically when you're doing some kind of tensorization type argument. And now the best arguments are you're sort of throwing down some random copies of graphs and then like filling in the final two colors randomly. So it actually seems like there's like a real genuine different structure in more colors. But there's this really fascinating mystery when R tends to infinity, right? We actually don't even know the growth rate here. So here we have this C, which is an absolute constant. So there's been a few papers of pushing up C, but here this is competing against an R. So the bound gets worse and worse as R gets bigger. You might hope that our bound here is getting better, bigger and bigger as r goes to infinity, but this is not the case. Right? It's getting worse and worse. Okay, good. Good. Actually, so this is maybe a good place to pause for questions, and then I'll start just like talking about the proof for the rest of the talk.
So yeah, maybe after this improvement, at least for this two-color Ramsey, what would you expect the truth to be? Well, it's below 3.8, but yeah, what should be the base of the exponent? Is it square root 2 or not?
I don't know. I used to walk around saying that it was square root 2, but just out of complete naivety. It seems like it seems like proving that r of k is at most 2 to the k is like a conceivable thing to do. Between 2 to the k and root 2 to the k, yeah, this seems to be quite confusing to me. So for example, there's this same gap even for the bipartite version of this problem, which is also, I mean, it's harder or easier depending on what the truth is, right? So this construction makes your life harder. It's easy. But yeah, like it seems like like this is a bit mysterious to me, and I actually really don't know. I mean, I know people that swear that root 2 is not the right answer, and and they laughed at me. They were laughing at me when I was sort of suggesting it might be. Yeah, but I would definitely conjecture that r of k is at most 2 to the k.
Okay.
That's I know it's only partially answering the question, but
that's good enough. Yeah.
Yeah. Okay, so the proof sort of starts with the following question, which is the obvious one, which is where is Erdős-Szekérys lossy, right? So we believe there should be an exponential improvement. Where is it losing? And you notice that in Erdős-Szekérys, we have a fistful of red vertices and a fistful of blue vertices when we're running this algorithm. And we're sort of paying for each red and blue. So even if you end up with a red clique at the end of the day, you've sort of paid for almost a complete blue clique as well. So what we'd like to do is sort of force our hand and say that we can take a bunch of blue steps, or sorry, a bunch of red steps, we'll use red, sort of right off the bat in the algorithm. And this was kind of the inspiration here, is we somehow want to ensure that we can stick with one color for quite a bit of the algorithm. So for example, if I took a random graph, if you actually give me just like a random coloring, I know right away, I can just say at the beginning, I'm going to go red. And now at every stage, I'm always going to be fine. I'm just going to half my vertex set. And so I can prove a bound of n is at most 2 to the k. Right, so this is the kind of thing that we would like to kind of emulate here. Okay, so goal, try to take lots of red steps in a row. You see, the picture we'll get to is a little bit more complicated, but I think it's good to have this in the back of your mind. Okay, so what does taking a bunch of red steps in a row actually look like? It looks like you're basically constructing the following structure. So I have a red clique. So say I take t red steps in a row. And now it's joined in red to all these vertices that I've kept here on this side here. And ideally, the size of this thing is going to be 2 to the minus t times the size of your world. And basically, this is what we're proving. So in this paper. So in the other paper, it was a bit more confusing. We dealt with different sizes. In this paper, we're actually sort of proving you can construct a book like this. Okay, let me put a little bit more detail in this. We're actually constructing a book where t is like some small constant eta times k. So it's like we're actually constructing like a sort of constant proportion, getting constant proportion of our way there. This is going to be 2 to the minus t. And there's going to be an error term as well, which is going to be something like 2 to the minus t squared over some constant, which is actually important, sort of importance bigger than 1. I think it's 8, if I remember correctly. So we get a little bit worse, but it turns out that this is actually acceptable. So this is basically the object we're building. I don't say anything about the coloring inside of here, right? And what we're going to do is just apply Erdős-Székely inside of here, right? So all I need to do is ensure that this confusing number here is bigger than R of K times K minus of K minus T, right? Then either I find a red K minus T here, in which case I can extend it to build the big clique here, or I just find my complete blue guy here. So this is the very high level strategy. Okay. I want to build one of these guys. And we do this with our modified, actually I was calling it the symmetric book algorithm before, like that. So I'll call it the symmetric book algorithm. Okay, so what I'd like to do is I'm going to now draw like a picture similar to like what we had for Erdős-Székely. It's going to be more complicated. And I'm just going to sort of like walk us around this picture and see what we can see. And eventually we'll see, in order for this to preserve this picture, we'll need to have sort of preserve some tricky properties. And then these tricky properties will lead us into this interesting geometric type problem. And then I'll say, okay, we can actually solve this geometric problem. And then I'll say something about how that feeds back into the algorithm and all that. Okay, so I'm just going to draw a picture and I'm going to sort of walk us around the picture a little bit. Okay, so here's the picture we want to maintain. I'm going to have this reservoir of vertices on the left here. This is where I'll be drawing the vertices that I put into my red book or symmetrically blue book. I should also say that I'm just going to stick with 2 colors, just because it's just more for me to write ... everywhere. But the point is, now this really generalizes completely naturally. So, I can just hand this to you and you immediately go and write down the R color version, all good. Okay, so here's the picture. So I'm going to have two sets, Y sub R for red, and Y sub blue for blue. Of course, if it's more colors, it's more blonde. And I have a red guy here. So this will be my A, and this will be my blue here. Okay, so this will be like what's called the spine of this book, what I had on the left here. And it will be joined completely in red to everything here. So this is sort of my book so far. In fact, I'll also insist that this is all red over here. This is my book so far. My red book so far, rather. Maybe I'll go light blue for the color blue. Okay, and symmetrically, I have the same situation down here. So this is blue, this is a blue clique, blue here, so this is a blue book here, and this is joined. I'm not sure if I said it, but this thing is called a book. This object is called a book.
Mm-hmm. And X, what is, you'll explain in a bit, but X meaning, is all the remaining vertices or it's
so X is going to be like my reservoir of vertices. So yeah, exactly. So X is going to be the reservoir of vertices that I'll add either to the spine of A or the spine of B. Okay, I think it's better to kind of go by example. So what I'd like to do is take a vertex in here, pull it aside. So I'll call this X naught. And I'd like to take a red, let's just assume I can take a red step with it. Okay, and I'd like to sort of figure out what that would mean for me to take a red step. What properties do I need to preserve? Okay, so I pulled a vertex out of here, x naught, and now, okay, so it's joined to some guys in red, here, and some guys in blue. Great. Okay, so what I'd like to do is put this x naught, say, into A. And I ask, what properties need to hold for this to make sense? Okay, so if I'm going to put x naught into A, I'm going to have to shrink x in order to preserve this bit of the picture here. I'm going to have to shrink x to be the red neighborhood of A here. Okay, this is fine. Basically, I just want to make sure that I don't shrink this by more than like some constant factor of the size of x at each stage. Because remember, I want to sort of I want a constant proportion of steps. So, I mean, I can't, this is going to start out to be like, basically n. So I don't want to lose more than like a constant fraction at each stage. Okay, let's not worry about too much. Okay, that's an easy thing relatively easy thing to ask for. But now here's the more complicated bit. I also need to maintain, I want this vertex here to have nice red neighborhoods over here, right? Because now I'm going to also have to shrink y of r to be just this bit, the red neighborhood of x naught, in order to maintain this property, that A is joined to everything in y sub r. Okay, this is sort of fine, and all basically I need is that the degree of x naught is nice. So I just need that this degree from x naught here is sufficiently large. Okay, so let me put some names on these things. So let's say that the red degree between here and here, or the red density, is p sub r. And symmetrically, I'm going to say that the blue density, sorry, this is from all of x. And the blue density between x and y sub b is p sub b. Okay. I'm definitely going to need to make sure that my red density doesn't shrink too much below 1/2, right? Otherwise, I have no hope I'm going to be, if I'm taking a bite bigger than 1/2 every stage, there's no hope I'm going to prove something as good as this. Okay. So sorry, let me just sort of try to make some notes about what I need. So to take a red step, I need one, that the red neighborhood, so x is a vertex I selected here, the red neighborhood of x naught intersection x is not too small. Okay, that was just this observation I had here. 2, I need that the degree here is big, but you'll just grant me that the degrees are regular across. So I'll just say that the density here has to be big. So the density across, which is I'll just write it so everyone is clear on this. So x yr divided by x yr. This is not too much below 1/2. Okay, and now 3 is really like the most, actually, sorry, let me do an easier one. Okay, so before I get to the hardest one. So if I put it here, I'm going to shrink the left-hand side to this, the red neighborhood. But I also need to make sure that my blue density between here and here doesn't drop too much in this step. So I need that the blue density, the new blue density, I'll just call it it'll be clear, I guess. I'll call this the new blue density after taking the step. So I put a prime. Also isn't hurt too much. But actually, again, this is not too hard to guarantee, right? If the degrees here are regular also to this bit in blue, or approximately regular, then this is okay. And it turns out that this is not such a hard thing to guarantee. Okay, so the real crux is the following thing. Now, when I take a red step, I shrink this to this. I shrink my red right-hand side down to this. And I want to maintain the red density between this bit and this bit here. Right, so this is really the heavy task because I'm shrinking both sides. So this is, I'll say the new red density has to be maintained. Right, so this now, I'll just write this for emphasis. This is the number of edges between X intersection neighborhood of X naught, red neighborhood of X naught, and the red neighborhood of X naught intersection Y sub R, divided by the appropriate thing. So X naught, Y. Good. Okay.
Julian, can I ask a small question? I don't know if it's timely, but so how do we get this initial, let's say, split into X, Y, R, Y, B? Just you do anything, or meaning is it important?
So just so there's one wrinkle that I've completely ignored here, which is what if the coloring you hand me as the density of red versus blue is slightly off. So say it's something crazy even if it's one half plus epsilon red, 1/2 minus epsilon blue for a sizable epsilon. This would actually be a problem because now I don't have this nice balance between these two colors. But this is actually okay because what you can do is you can just start by taking a bunch of Erdős-Sekere steps.
Mm-hmm.
And then the colors will rebalance, and you've only been winning in that time. Yeah. So you need to do some preparation. The second thing is, okay, now assume your colors are balanced. Then just take a random split is enough.
Mm-hmm.
So I have it. Yeah, there's a slightly different formulation. I'm sort of saying it slightly differently than proved in the paper. And instead of maintaining density across, we maintain kind of this minimum degree across. But in a way, it's a little bit, we're a little bit tricky there. But you can completely make this picture work. So even if you give me this picture, do a random partition, if you have some vertices that are a little bit if the degree is quite not regular, you can actually regularize the degree, and it only helps you because you'll only get a bit of a density boost in one of the colors, which is actually something our algorithm, I haven't got to it yet, but something our algorithm deals very well with. Mm-hmm. So there's multiple ways. These are all good questions. And you have to be slightly careful with them.
Yeah.
But so I'm sort of trying to get to the biggest obstacle, the biggest, most painful obstacle, right now, which I claim is this 4. Right, 4 is a little bit like a regularity type thing, right? I'm passing to a subset on the right and left, and I want the density not to be hurt too much. And of course, where there's no way we can use regularity, it's just that's way too inefficient to get any kind of bound.
Mm-hmm.
Okay. Is there any other questions at this point?
Why do you have in second point? Why do you have some density? Instead of something like first point? Well, if you say that you want to shrink Y not very much. It looks like you need to have a big red neighborhood of particular x0.
Yeah, right. So you're saying basically, really, what you need is a good min degree condition rather than a density condition. Yeah, this is
just min degree. So you can guarantee that every vertex in X has big red degree and with red part and big blue degree with blue part.
Yeah, exactly.
Not average.
Yeah, this is what Julian was commenting, that actually both ways are possible, working with average degree or with min degree, I think.
Yeah, so actually in the paper, we do explicitly work with minimum degree, for example. Yeah, actually, sorry, I should say, so in the first paper, we do density, and then there's a step when we do regularizing of degree. But when you're doing two colors at once, yeah, I guess as you point out, it's not, you have to be a bit careful, right? Because you could have large density in one color and larger density in the other color, and it's not clear that there exists a good min degree condition in both colors. So when you regularize one way and the other, you could be left with nothing. Yeah, you're right. So in this particular version, you have to be a bit more careful. So actually, in the paper, we're working with min degree. I just thought maybe density was a little bit more just like intuitive, sort of global property. Okay. Any other questions at this point? Okay, so maybe I'll push on. Feel free to interrupt at any time. Okay. So yeah, so it's this fourth point that I think is really as I mentioned, the crux. And in some sense, when you look at this picture, it seems like there's something really to guard against. Because what if your enemy just hands you, the picture when, everything here is blue and everything here is now red, for example. So this is kind of the extreme of the situation when your densities have gone wrong, and now there's no possible step you can make. You might think, oh, you can switch colors or something, but then you're kind of in this error situation when you're swapping sides. And our efficiency is very much about not switching colors. We're trying to stick with the color and hold on to the density. Okay, so here comes the geometric kind of picture. So I'm going to redraw this picture, and I kind of try to tease out this geometric. So okay, so let's just draw this y of r. Okay, and then there's the other side y of blue that we don't really care about so much at this moment. Okay, so what happened? I had a vertex. Okay, and here, this is somewhat of a typical vertex. And I looked at its red neighborhood. Great. So here. Now, let's consider some. So what was the problem? Is when I looked at the neighborhood over here, the red neighborhood of this vertex over here, that the red density between here and here dropped. So it is smaller than typical. Okay, what does that mean for a typical vertex here? Okay, notice, actually, let me make another observation. Sorry, let me just observe. So if I have some typical y chosen in this neighborhood, red neighborhood, what does that mean? It means that, well, I'm assuming that the min degree is nice and controlled over on this side. So its min degree over here is nice and meaty, nice and 1/2. But in order for the density to drop, these two neighborhoods are sort of repelling more than they should, right? So they're particularly unfriendly. And moreover, I don't just have this for a typical. Remember that I'm allowed to throw out all but some small constant proportion of my neighborhood. So even if like 99% of these guys have this sad, unfriendly property, I'm still happy. So it's sort of when I have like 99.9% of my guys are unfriendly and I can't pass to this nice subset. But now we're kind of in this very interesting scenario, right? I have for every pair, like for every sort of, almost all pairs, we have nice, good density to the other side. But the neighborhoods are repulsing sort of much more than they should. Right? This is the feeling here is that this is sort of an unusual circumstance. Yeah. Okay, so what I'd like to do is sort of phrase this now as like a geometric problem, something to kind of get our geometric intuition going. So here's our model problem. Yeah, let's say model problem. Okay, so I have all these like neighborhoods. So I have all these vertices x and x, and what I'd like to do is now associate each x with a vector. Let's say u sub x that encodes its red neighborhood, and a vector v of x that encodes its blue neighborhood down over in this blue land here. Because of course we're always playing these two games at once. Okay, so it's actually a very simple kind of thing. I'm just gonna take the characteristic vector, rebalance it, so I recenter it, so it means 0, and just like rescale it. So it's not super important, but since it's so easy, I'll just write it here. So it's just the indicator of the neighborhood minus the current density times the all ones vector. And now I want to just rebalance it by the kind of the standard deviation if it was just a random thing. So PR times, I guess the size of YR. Okay. I guess I could write this as the indicator of the red right-hand side. Okay, and similarly, V sub x is now just going to be, oops, this is going to be, sorry, the red neighborhood intersection. Okay, this got a lot uglier than I thought. Okay, but basically the neighborhood that we're thinking about here. And then this is going to be the same, but now with the blue neighborhood. Okay, so this is neighborhood of blue, x intersection y blue, blah, blah, blah. Y sub blue, blue, y, blue. Okay, it's not so important. The point is that we have these vectors that have this sort of interesting property. So this property of having this repulsion, this unfriendliness. So what does this mean? So if this unfriendliness is now going to be like a sort of familiar looking geometric property. So if I look at the red neighborhood intersection, the red neighborhood, because it's all happening on the right-hand side. Right, so if this is like smaller than PR squared, like 1 minus epsilon, maybe I'll use lambda actually. Times, so this is just times the size that we expect. What am I calling things here? Y, yeah. This will hold if and only if, I have the scaling slightly wrong. Okay, I might as well write a true statement. That's fine.
So you want the scalar product to be negative or something, right?
Yeah, sorry. I just wanted to write the right constant, which I may or may not succeed at here. Yeah, so bear with me, friends. Yeah, so if and only if this is like negative lambda or something like that. Yeah, right. Okay. Good. Okay, so this is all this encodings and doing. So what's kind of the model problem that we're working up to is the following. So I have a collection of vectors, u of x. Let's just renormalize them all nicely so they're on the unit sphere. It's actually not super important, but I just find it useful for intuition. And I have, so this is x and x. And I also have this corresponding collection of vectors also on the unit sphere. Right, so these vectors are actually not even talking to each other, except for the fact that they are joined, they have the same index set. Sorry, let. And suppose they have the following property. Okay, so that u of x, sorry, shoot. How do I write that? And suppose that for all but, now I'm always allowed to throw away some small delta proportion. So I need that to appear somewhere. So this is all but delta proportion of pairs. And we have u of x, u of y, less than, say, minus some constant over root n. Okay, so these are points on the unit sphere. They're typically, if they're just random points, their inner product is varying at the scale 1 over root n. But now I'm interested in this event that they're macroscopically negative, like sort of on the scale of their standard deviation. This is negative, or Vx comma Vy is less than minus C over root n. Okay. I'm not quite finished, but let's just try to digest the property so far. So the property is, the assumption is, suppose that I have, every time I look at, okay, there's going to be some delta pairs excluded. But for all outside of this set, if I look at this pair, either the u vectors are macroscopically negative, or the y vectors are macroscopically negative. So it's this funny thing when it's like, if you imagine the graph, there's like kind of like two graphs on these sets of points, right? So one graph is the graph where one is a negative, and there's another graph where you join 2 points when the other is macroscopically negative. What you want to say, this property is sort of like you can put them together and cover almost all the pairs, all except for delta pairs. Okay. Of course, this is actually possible to create pairs like this. And one way is to just take like a simplex in like 1 over a delta dimension. Because then basically, just like even let the u's be like a simplex, then actually one of these two properties will hold almost all of the time, right? Because they'll be just negative so much.
So basically, you mean take a simplex and then duplicate the points, the vectors, right? So basically, take many copies of each vertex.
Yeah, exactly. Or like cluster, even like more generally cluster around
clusters.
So this is kind of what the conclusion is going to be. There's more complicated examples of this actually, but what the conclusion would like to be is like, if I have this property, then I exhibit some clustering. And we'll see what that means exactly in a second. So if I have this, then either this ux, fraction of ux is clustered, or the Vx are clustered. Like something like you're clustered around a simplex or something like this. Okay. Any questions about this? So what I'd like to state, sorry, let me just say, so where this all fits in to this picture. So this situation is similar to what we were having, the situation that we were sketching up here, right? This is encoding this situation. But now I'm sort of looking at the red neighborhood and the blue neighborhood at once. So I've looked at the red neighborhood. Okay, but I could also look at what's happening in the blue neighborhood, right? And if I need to have the same behavior, not between here and here, but between here and here, and if I didn't have this funny behavior, I could just take a blue step instead, and I would be fine. Okay. Good. So I can sort of assume I'm in that situation. Why is the conclusion any good for us if U of x and V of x are clustered? This clustering, what is this going to mean? This is going to mean actually you have a bunch of inner products that are much larger than you expect. And what is this? This is going to basically translate to, I could find some set of vertices over here on the left-hand side, and some set of vertices over here where the density between here and here is actually a little bit larger. So here I'm not taking a red step or a blue step. I'm taking a density boost step. I'm just saying, okay, fine, I can't win. I can't proceed with my argument, but what I can do is I can increase the density, and that's going to be useful later. So there's a fine sort of calculate, but you have to be a bit tricky about what counts as a good density increment. But I don't want to focus on that. I want to talk about this new geometric problem here. Okay, so let me just now state the formal lemma. I'd like to say something about its proof, and maybe even say this sort of yeah. I think that's a good place to stop probably. Okay, so here we go. And again, I'll just remind you that everything here, so I had two sets of points. Everything is going to be fine for R sets as well, so it'd be different. Okay, so here we go. Let's see, let the U of x and V of x be sets of points. It turns out here, actually, the scaling doesn't really matter. So I'm just going to say at R to the n, the precise way that we have it. Good. Then there exists some parameter lambda, which is at least -1, such that one of the following holds. So either we have A. Okay, so here I'm just gonna go to a probabilistic notation. So here I'm thinking of sampling X and Y just randomly from our vertices. Okay, just randomly, uniformly at random. Nothing fancy. It's just useful to switch the notation here. Okay, I'll just maybe just write this and then I'll talk about it. So just a little bit long. Vx, Vy. It's this one. Yeah, this is like some constant e to the minus constant roots. Yeah, plus 1. I guess these are different. Okay. And the second condition is just the same thing, but with the u's and the v's reversed. So this, I'll just get to, I'll come back to this in a second. So this is just Vx, Vy, big lambda, and Ux, and same bound here. Okay. Okay, let's unpack this a little bit. So you give me some collection of vectors, u of x and v of y. And now I claim the following. Oops. Yeah. Okay. And now I claim the following. There exists some lambda, right? So as possibly as small as -1, but possibly very, very large as well. So that let's just focus on this condition, so that the probability that these inner products and or at least lambda and these inner products are at least -1. Okay, so -1 here, this is encoding where I'm no longer happy. So if you're below -1, that's too much repulsion for my algorithm to accept. Now, what is this saying? Okay, actually, even let's just think about lambda equals -1 for now. Say the algorithm gives you -1. It says that a good proportion of points, right? So now this is just going to be an absolute constant here. So this is going to be 1, and then now this is just some small absolute constant. So this says that a good proportion of my pairs are healthy actually in both colors. Okay, so what would I do, going back to the algorithm? Now what I do is I just choose some x for which this holds. So this is my x. Pull by some x naught here for which this average holds for all y. And now I can find some subset x primed. And each one of these guys here have these inner products. The corresponding inner products are not too negative. So that means if I look at the red neighborhood of this guy and the red neighborhood of this guy over here, that's not too repulsive. And the blue neighborhoods over here, I guess this would be a good moment to use colors, but I didn't. Oh well. The blue neighborhoods over here are not too repulsive. And then what does a step in the algorithm look like? I take this x naught. Now I look at the colors between x naught and this x prime. If it's majority red, then just go red, right? So I pass to a nice, healthy constant fraction of these guys, and I take a red step, right? And now I know that the degree here is nicely behaved. Okay, likewise, if this is majority blue here, this other property here gave me that the blue neighborhoods, oh my God, the blue neighborhoods over here were not too repulsive. And so I could take actually a blue step. I could put a guy into my blue book.
So this x naught is coming from x prime, right? Or x0 is coming from x.
Sorry. It's not. It's coming actually just from x. So I'm fixing some x, and now y. So I'm sort of thinking of this as like taking this expectation outside here, right? So there exists just by math, there exists some x for which this probability is at least a constant.
Okay.
Right, and now each of those y's that corresponds to this set, this x prime set.
Okay. Because before it, and one more question. So it looks like you want to normalize x in some way or another, because this one scalar product bigger than vx. I mean vx, vy, ux, uy, or you refer really to the vectors before, these characteristic vectors, you mean?
Yeah, exactly. You're applying it to this recentered characteristic.
Because what I mean here is that, so you say the statement for any vectors, but this -1 condition would look very like scalar product at least -1 would look very different if you are long or if you are short. No, so there should be a difference.
Yeah, I agree. I think it looks a bit strange, right? Because you're. It seems like basically these things depend on your scaling. But actually the lemma is still true, because actually your probability bound also will depend on your scaling. So it's a bit odd, but it's actually okay. So
No, but you can. What I mean is that
okay.
you can rescale UX and VX. Just imagine that this you want to prove this lemma for some UX VX. Just take million times each vector,
Yeah.
and you don't have to change the lambda. You just apply it for the million times the vector. You get some bound depending on this lambda, but then you can go back to the original ones and you would get 1/million there for free, kind of, no?
So you have to. So you'll get a bigger win, but you'll also potentially get a bigger loss if you rescale everything, because now this is like this fixed -1. So now if I take this step here, I'm going to lose sort of 1,000,000 times more than I did. So so it's so this actually really comes into the proof. And we actually do a rescaling like you suggest, because we actually care about how, like, I didn't say anything about how much, like, where do we care how much we lose? And how much you lose depends actually depending on where your density is. So if your red density actually is a little bit higher, then you're feeling very rich, and you're feeling like, well, I'm much happier to lose more red density. So actually, that's exactly what we do. Is you can rescale by some larger number, and that corresponds to like losing more, but it also corresponds to winning more in the other case, which is important. Like if you just run like a flat density increment argument, you'll never make it to full density, because there's just not enough steps in the algorithm. So we have to do this kind of like dynamic thing, which is like if your density starts going up, you rescale. And so either if your enemy hands you a density boost, you jump by more, but you have a little bit of win, so you can afford the loss that you get. Yeah, you're quite right. This rescaling has this nice property.
Interesting. Still, I mean, this -1 there, I mean, it's a little bit like that. It's lambda and -1, not lambda and minus lambda or something. I don't know. It's
it's a little bit strange. Okay, let me just say so. Okay, so this is right. So the lemma hands us this lambda that we have to deal with. So this is basically what happens if lambda is very small. And in fact, that we have the same argument if lambda's, between -1 and some fixed parameter. In the case that lambda is bigger than this, like it could be that the lemma hands you this very large lambda. Like for example, if you feed a simplex into it, is one of the point sets, it will find this huge, this kind of huge spike in the distribution. So in this case, what do we do? So say again, we're just in the first case for simplicity. The two cases are being symmetric. And again, this is what we do, right? So it's like now we take this x naught aside. You take this collection, like as we did here. There's going to be a set here of size e to the minus root, basically minus lambda times x. Oops, sorry, that looks ugly. Root lambda. This e to the minus root lambda size subset here. And what do we know about this subset? Is that all the red neighborhoods actually correlate. So let's fix the red neighborhood of x naught. All of these neighborhoods actually correlate a lot. We have the opposite situation. They're very friendly. And this is actually a density boost, right? So my boost is going to be take this subset here and take the neighborhood of x naught on the other side. So this will be x, and I'm going to take this x prime. And now what I've passed you a subset and given my red density a boost. So then this is And the trade-off here is basically that this e to the minus root lambda is like an acceptable loss. So basically what you need to do is beat exponential here. So we get like an e to the minus root. So this is more than enough. Nice. Maybe I'll just say something about the proof of this lemma. Okay, I mean, this is like kind of the sketch of the entire proof here, except for the proof of this lemma, which is also quite nice, and actually kind of surprisingly simple. So let me just quickly give some intuition for this proof here. So what we want to do is define two random variables. I'll call it u, which will be, okay, I'm going to sample, sample this v sub x. So I'm going to sample randomly a pair, x and y. So x, y are just going to be uniform in x. And now I consider the following random variables. So just the inner product of vx, vy, and v is just going to be, oh, whoops.
Tricky notation.
That would make a lot more sense. You call it like this. Okay, right, so these are two like very coupled random variables. And one thing to notice here is that if you look at the expectation of v, this is always non-zero. And similarly for y, right? So I just take, I can write this expectation y, expectation x, and now this is a bilinear business, so I can just bring the expectations in, it's just I'm gonna get something positive. Okay, by extending this kind of thinking with a little bit more work, you can actually realize that all of these mixed moments are actually non-zero. Using kind of like a very simple tensorization argument. And actually, this is the property that we're going to use. So what's the picture? Like here's my UV space. So this is say U, this is V, whatever. And I'm sad if, like I'm sort of sad in this region here, right? If one of these is much less than U or V. Okay, and the idea here is we want to find a function, a kind of test function, f, with the following properties. So A, I want it to be, so this is my like unhappy region here. I want it to be smaller than -1 in the unhappy region. It's some sort of kind of bump function type thing, right? So you want f not to grow too quickly. Right, so we know all the moments are positive, right? So we expect a lot of mass over here, but we don't want a lot, kind of a negative mass here to be balanced off by some very, far away mass there. So we want it not to grow too quickly. And C, and here's kind of maybe the magic ingredient to use these guys, is we want, when we look at the Taylor expansion of these guys around 0, so this is like Cij, Xi, Yj, we want all these coefficients to be non-negative. And basically the proof is now, if you can find such a thing, let's argue about the proof. So you look at the expected value in these funky random variables, like these are kind of the mysterious thing, of f of uv. Okay. Notice that by this, all these moments are now positive, so I can immediately conclude that this is bigger than 0 by this fact I told you up here. Okay, so now let's try to bound it from the other side. Now, on the sad event, I am always at most -1. So I'm getting at most -1 on the sad event. On the happy event, Okay, so now I just want to, let's just assume that there's some point that basically approximates this from above. So some lambda. So the probability, say, U is bigger than lambda. Sorry, no absolute values here. Okay, or vice versa, right? It could be another term. Times the value of this function f, but I told you it doesn't grow too quickly. And here, surprise, surprise, I want something like at most e to the root, like e to the root, the size, right? In the variables. So something like this. So now I'm going to get some behavior like this. I mean, constants abound. And now we see we're basically done because this whole thing is bigger than 0. Right? I can assume like the sat event is bigger than a half or something. Otherwise, I'm just done, no problem. So now just bring this over to the other side, divided by e to the root lambda n, and I get exactly this event here on the other side. That's it, right? So this is exactly giving me basically this conclusion here, since this is u and this is v. Okay, so maybe I should stop there for today.
Well, thanks a lot, Julian. Yeah. I don't know. Maybe I'll clap. I don't know. Maybe somebody will join. But how do you construct this function?
Yeah, right. So how do you construct it?
It's you told us almost everything. Stopped at the culminating point.
Yeah. So the idea is if it's not that crazy, but so it requires an idea. So if you consider e to the root x, then this function sort of looks like approximately appropriate, right? Because it's growing not too fast, right? The kind of growth I want. And when x is negative, or maybe I should just give you, it makes a bit more sense to think about that, but when x is less than this -1 in this bad region, okay, it's not negative, but it's kind of close, right? Because now all of a sudden it's bounded. Okay, it's complex and everything, which is a bit annoying, but it's bounded. So the idea is to kind of like use this to build something. So f at the end of the day is the following. xy is like x times 2 plus cosh root y plus y 2 plus cosh root x. Like this, where cosh root x has a Taylor expansion that looks like this. So this is n over 2. Right, so now you see right away that this has all positive coefficients, and you can check that it has this nice property that you want. So like this is a little bit magical that there's such a thing exists, but it kind of makes sense that this kind of thing should exist based on these things that look close and you can guess pretty quickly.
Yeah, very, very elegant. Actually, the argument, I liked it a lot, this part that you just, so you just come up with a test function that does what you described. It's a very, very elegant move, I think.
Yeah, so something that's interesting is this property of all positive moments seems very natural one, yet not one that I've interacted or seen any theorems about before, if I can remember. So yeah, maybe somebody here knows. I'd be keen to hear about it if they want to email me or chat later.
I mean, it was superficially it reminded me some things, but
It reminds me a little bit of actually Russian analysis in like the 90s. Like they have complex analysis. These things about like if you have a random variable and you know that your like probability generating function is like analytic everywhere, then you can say some nice things.
Mm-hmm.
It's not quite the right thing, but yeah.
Nice. Yeah, it's very nice. And is it like, so qualitatively it gives you what you want, but is it actually like, how good is the clustering that you get? So my understanding is that out of it you get, let's say, one cluster, right?
Yeah.
Of points clustered around X. Is it like more or less tight on the geometric examples, like like the simplex that you described, or
Right. I think the simplex you get even better clustering. Your tails are like 1/λ. I'd have to just double check all the. But I
yeah,
think
but I mean probably there are for
lambda.
yeah, but
Definitely 1/polynomial.
yeah,
lambda.
1/polynomial, but maybe there are more complicated examples. I don't know, like.
Yeah. So there are more complicated things. So let me think for a second. Yeah, so we have this other geometric conjecture that we thought about for a long time, which is a bit different. So I think you can maybe tweak some examples there. But I mean, I can say something, but this is not enough. So like some examples that were confusing to us in general and might be relevant here are things like this. So I sample x1 up to x like root d in, let's just say -1, 1 IID. And now you define this kind of like symmetric tensor thing or whatever. So like
You
your
mean
random
-1
variable.
1 to the d, or no? Or no, it's really -1 1.
Yeah, sorry, I meant just. Yeah, I guess I could just say something like that. Yeah. And I lift this by looking at all pairs, like non-equal pairs.
Mm-hmm.
Yeah, so what's like a bit weird about random variables like this is like if you look at x, y, or like IID samples of this, of this guy, and now you look at their inner product, it does like weird things. Like the probability, it's like say just less than 0 is like bigger than a half. I don't know the number off the top of my head, but say it's like 0.6 or something like that. So the distributions have this funny kind of skewed property where there's like more mass here. Yeah, don't quote me on this value, but it's definitely bigger than a half, which is probably.
Mm-hmm.
So I might go sniffing around something like that for example. But yeah, I think like understanding what's going on here a bit better numerically, I think is really interesting problem. And also like this, like it gives you these kind of things that were like clustered enough for us, but like, yeah, what if you like to say a bit more about, right? Like, so a simplex, of course, we know that we have a set for which every pair is clustered.
Yes.
Which is quite a bit stronger. Yeah. Yeah, so I think these are all lovely questions, and would certainly be interested in, and I suspect could have applications here and elsewhere.
Yeah, this is very interesting. Cool. Any other questions?
Hi. I want to ask you some question. Does your proof also provides an algorithm polynomial in the size of the graph that finds the clique of size of k, or there is some non-constructive steps when x prime appears?
Yeah, I think the way it's written, there's technically averaging and things going on, but I don't have a great intuition for these things, but I suspect they can be dealt with. I suspect everything's polynomial time. There's like it's like randomness, but I know there are yeah, I suspect it's a polynomial time algorithm. Yeah.
Okay, thank you.
That was very interesting. It's actually, I liked several things. And this geometric lemma in particular, I like these statements about scalar products of vectors. It's very interesting.
I feel like there's more to do here in developing this perspective. Yeah.
Yeah. Distanzarization also, yeah, I mean, I immediately think about this Borsuk's question. And
so basically it is it's this example.
Yeah. And but I wonder if this property that you talk about, maybe it can, I don't know if it's relevant, but there the problem is treated in a way that it's like symmetric kind of. Maybe this suggests that one has to look more into it and understand better what's going on in the scalar product. Yeah, well, anyway, I don't know if no more questions, then yeah, thanks a lot, Julian, and yeah, bye.